Here's a model of a car I made in Python. You can accelerate, brake, or gradually turn the steering wheel of the car. To realistically maneuver the car, let's take some inspiration from reality, where you typically only turn the car's front wheels. Extending two lines perpendicular to the four wheels of the car, the intersection of these two lines gives us the point around which the car turns. The car essentially drives in circles, and we can define a turning radius from these two lines. The car also measures 5 different distances to the track edges, 1 to the front and 2 to each side. These sensors give us some information about the vicinity of the car, and the goal is to give the car some way to sense its environments. Now, given these 7 different parameters, the speed of the car, the wheel angles, and the 5 different distances, what I want to do is make the car model self-driving. So we're going to define an agent to drive our car. Now, there are many different ways to optimize an agent. You could, for example, use evolutionary algorithms. This branches out into genetic algorithms, swarm intelligence, and a lot more. What I see a lot of people doing in similar projects is to use genetic algorithms. And that works, but genetic algorithms require a population of agents, and they can be computationally inefficient, and I think we can do better. What we could instead do is to use reinforcement learning. 2 viable options here are deep Q-learning and policy gradient. You can even combine the strengths of both methods and get actor-critic reinforcement learning, which in turn branches out into several different variants. But for this project, deep Q-learning is going to be sufficient. And to understand deep Q-learning, we're going to introduce neural networks. This is a neuron, a simple computational unit. It consists of a weight W, a bias unit B, and it takes an input which we'll call X. The neuron multiplies the input with the weight, adds the bias, and lastly, applies an activation function. This activation function can in principle be anything differentiable, but a popular choice is the so-called ReLU, or rectified linear unit. The neuron can also take several inputs, in which case we also add more weights, and we can now represent the output with the help of a dot product. Now, even if the inputs aren't technically neurons, it's popular to also draw them in the same way. If we have several outputs, we need a vector of bias units, and we need a matrix of weights. We can also add a so-called hidden layer between the inputs and the outputs. This is actually one point where the activation functions come into play, because if we have linear activations, this is the same thing as a single matrix multiplication followed by addition. So adding a hidden layer with only linear activations is quite useless. Now what we have here is a simple neural network. A neural network with more hidden layers is called a deeper neural network. A deeper neural network can typically learn more complex patterns. But how do we get it to learn in the first place? We now need to introduce loss functions. For our purposes, we can use the so-called mean squared error as loss. Here you compare a collection of known observations y true with the predictions of the network, which we call y. You take the difference between all observations and their corresponding predictions, square them, and then find the average. In the simplest possible case, we only have one neuron without a bias. If we take the derivative of the loss function with respect to w, we know in what direction to change w in order to minimize the loss. To do this, we define gradient descent. Here, we iteratively subtract small parts of the derivative from w itself, and w gradually gets a more optimal value. Let's look at a very simple example. Assume that we have a bunch of data points which are approximately linear with respect to x. We randomly initialize w, and our single neuron defines a line through the origin. It obviously has the wrong slope, so we begin taking steps with gradient descent. If our step size is too big, we begin seeing oscillations. Then we can decrease the step size and we get a more stable optimization process. When w gets close to the optimal value, we can decrease the step size even more to fine-tune it. When we add a bias, which also gets optimized, This corresponds to shifting the line up or down. This is the basic principle for optimizing most neural networks. If we have bigger neural networks, the optimization problem is a little bit more involved since we have a multitude of parameters to optimize, but the core principle is still the same. At the heart of Q-learning lies the Bellman equation. It says that the so-called Q value at the time t, given some state st and an action at, is obtained by the discounted expected sum of all future rewards. The discount factor gamma is somewhere between 0 and 1, and a lower value means that you focus more on rewards that are closer in time. A reward is high if you take a desirable action given your current state, and low if you take an undesirable action. If we expand this sum, the last term gives the Q value at time t plus capital T. Then we can simplify this part as the Q value at time t plus capital T minus 1. And we can keep on doing this until we just get 2 terms. And we also choose actions so that rewards are maximized. This expression is a lot easier to handle. At each time step we can store the initial state st, which action we took at, and the new state that this action led to st plus 1. And now we can define a loss function. So if we want this equation to hold, we want both sides of the equation to be as similar as possible. So then we can take the difference between them and square it, so we get the mean squared error. In practice, the way that we choose actions in Q-learning is often through an Epsilon greedy policy. According to the policy, we choose a random action with probability epsilon, and the action that maximizes Q values with probability 1 minus epsilon. In early generations, we choose a high epsilon to promote exploration. At this stage, our model basically just predicts nonsense anyway. As our model gets better and better, we choose a smaller and smaller value for epsilon. To define the model state st, let's use the 7 different parameters that we introduced in the beginning. First, we have the 5 different distances to the track edges. Then we also have the angle of the front wheels and the current speed. Our outputs are going to be the Q values for each possible action. The actions correspond to changing the speed of the car or changing the angle of the front wheels in either direction. We can make a simple neural network by connecting the inputs with the outputs. But in our case, we're likely going to need a couple of hidden layers. And now we have a way of mapping states and actions to Q values. But for the Q values to make sense, we need to introduce a reward system. To do this, let's first look at how tracks are designed. A racetrack consists of a collection of several nodes and 2 borders to the sides. Every time the agent drives the car past one of these nodes, we can note how long it took for it to pass from the previous node to the current one. So let's say that these blue dots correspond to the agent driving the car past one of the nodes. We can take the reward as the inverse time between these 2 nodes. And when the agent crashes, it's punished with a negative reward. But there's nothing really special about these track nodes, so to get a smoother reward function, what we're going to do is to also interpolate between the timestamps. To give an example of how this might look in practice, here's me driving the car. As you can see, when I'm driving the car faster, it tends to get high rewards. But when I crash the car, it gets a negative reward. Now all that remains is to actually train the agent. What I'm showing you here now is the performance of the agent at specific generations, and the agent never sees this test track during training. In the beginning, the agent performs poorly and crashes very quickly, but it doesn't take long for the agent to learn good behaviors. For example, the agent quickly realizes that driving the car fast is beneficial for maximizing rewards. This is clear in that the speed bar seen on the screen is almost always saturated. In later generations, the agent also learns that driving the car straighter in the curvier parts of the track is more beneficial. Now let's look at a few examples of what the agent can do after training. I added a couple of things, such as drift tendency, so the car can actually start to drift if this is high enough. I also added the possibility to change the acceleration of the car or the maximum turning angle. And the agent is actually surprisingly robust to all of these changes, despite having them fixated during training. I wrote a multi-agent simulation game, where each agent is controlled by the same neural network. And I accomplished this by extending the functionality of the sensors, so each car can actually sense all of the other ones. And this was pretty cool, because at some points you can actually see some agents overtaking other ones. And you could probably use this in actual racing games, with AI opponents controlled by actual neural networks. I would find it quite awesome if in the future we could have video games where our surroundings actually learns from us, actively with reinforcement learning. And I might actually have something similar to that in the pipeline. So subscribe and stay tuned for upcoming videos.